You guys have about 5 minutes to go through these, and then we will start the day. All right, let's get started. So we are making an ether in this first one here. Our nucleophile is going to be this alcohol here. We're going to start with our carbon skeleton. We're adding to our double bond. And we said this is our nucleophile, so this is the portion we need to add. We're going to lose that H and just get this here. HBr will degrade our ether. We're going to degrade at both places where we are bonded to this oxygen here. So on one half of our ether, we should end up with a bromine where our oxygen one would have been. Same thing on the other side. Plus a water. MCPBA allows us to make oxides. We are in we have an aprotic nucleophile here. We have Na ethoxide. So this is going to open at our less substituted position. Giving us an alcohol at our more substituted position, and then this OET at our last here. HBr is going to give us our protonated epoxide. We have this doubly substituted on the left here, so this is going to follow the rules where it's going to come in and attack at our more substituted center. So our Br can come in open our epoxide the other way, where we're attacking our more substituted center. Alcohol will be left over on our less substituted. Br will be here on the more substituted. Gonna run out of space, so I'm gonna rewrite these on another page. Okay, our first one, we have aromatic ring. So the aromatic ring is not going to degrade at all. We are going to keep that phenol group. But the other half of it is still going to fall apart. So we'll end up with a chlorine and this alkyl halide here. All right, Grignard is a protic. So it is yet again going to open on our less substituted center. Let's do water. So these lone pairs from our Grignard can come in, attack at our less substituted, opening this up. We'll get an alcohol in our more substituted center, and then the addition of these 3 carbons here. We've got another one where we are forming the epoxide and then opening it. So MCPBA, give us our epoxide. And then our next step, we're to come in with NaCN, which is again a protic. So our CN can attack at our more substituted center. And give us this alcohol. Our last one is our example where we are dealing with a less substituted epoxide. H plus this alcohol here. we have a secondary center next to a primary center, as opposed to a tertiary one like we typically do. So this is actually going to follow the rules where if this is only a secondary center, this is going to come in and attack at our less substituted position. And give us this ether here. So yeah, as a review, when we have these less substituted ones, even if you're an acid, it's still going to open at your more substitute or less substituted position to give you this product. Okay, today we are going to talk about something a little bit different. I'm going to start with some molecular orbital theory, which is going to really start taking effect in reactions around either Wednesday or Friday. But the book kind of jumps around a little bit when it talks about these, so I'm going to follow the general pattern it uses. So let's start with 16.1, which is talking about different types of dienes. So a diene is exactly what the name sounds like. Ene, like an alkene. And then di, like two. It's something with two double bonds. There are technically three different types. Two of them are very similar. So the first type is cumulative, accumulated. And this basically means that they're on top of each other. So if we have a double bond that looks like this here, where we have basically this dot is just a carbon, by the way. Anytime you see that, that's a carbon. There is no space between these double bonds. So if you draw out the molecular orbital diagram for these, the way that they have to be stacked is going to look like this. So we're going to have one double bond on the top. Hopefully you guys have seen these kind of drawings before. This is a pi bond. And essentially that is like, that's your double bond. So you have a sigma bond down here, which is your regular single bond, and then your pi bond up on top here. In order to have two double bonds that are on this same carbon here, one of them is going to be going up and down. The other one is going to be going in and out of the plane. And it's going to look like this. We can't have them both on the same position, or else then we'd have too many electrons on this carbon here in the same spot and be kind of a mess. That's when you have usually a negative charge next to a double bond would be the equivalent of that. So these cumulated ones, they're kind of stacked, similar to how a triple bond is stacked. And these have no resonance to them. The electrons from this double bond that is going up and down can't make a 90-degree turn and jump into the electrons that are going in and out of the plane. So these are isolated. which brings us to our next one. I'm going to do these out of order from what the book says. So the other type that they show is isolated. And this is where you have an sp3 center in between. You have a pi bond here, a pi bond here. There's an sp3 center in between them. They can't make this jump here. So these are isolated. There's no resonance also. Our last type is going to be conjugated. And as you might have guessed, these do have resonance. So we have this where they are essentially spaced out. They're not on top of each other. Our pi electrons are going to look like this, where they all can be nicely lined up in the same plane. This has resonance. Or at least it does right now. Okay, so when we think of these systems here, they're drawn like this. This is actually one of 4 potential options that we can have. So for a system with 2 double bonds in it, all these markers are struggling today. Dark blue. This is what's called a 4 pi electron system. And all that really is the number of double bonds times 2. So each double bond has 2 electrons in it. We have 2 double bonds. So that's a total of 4 pi electrons here. There's also 4 positions that have pi electrons, which would be 1, 2, 3, 4. If I had something with like this, I still only have 1, 2, 3, 4. Those are the only spots that have a double bond. So those are 4 positions that have pi electrons. Okay, so the one that we just talked about is going to be our lowest energy configuration. And that is when, so these are orbitals here, all of the electrons. I'm going to fill in dark for where there is electron, are occupied on the same plane. So this would equate to something that looks like this here. This is drawing it onto our carbon skeleton. We could also draw it as this. I'm going to write with resonance. As we add energy into the system, we're going to start flipping these orbitals. So the easiest one we can do is where we have a pair of 2 on top for 1 double bond, and then a pair of 2 on bottom for another double bond. this is going to create what's called a node. And essentially a node is a place that electrons can't move through. So if I redraw this, here, now we have one double bond that is on the top and another double bond that is on the bottom. And it's a node because the electrons that are on this bottom one can't do a 180-degree turn in order to get to this top one. So this no longer has resonance. We still have two double bonds, but in this case, we are resonanceless. As we add more energy into the system, we create more nodes. So our next one is going to be a single electron by itself, a double bond, and a single electron by itself. We now have two nodes. It's going to look something like this here, or this where we have two radicals on the end and then a double bond in the middle. Our highest one is where we're going to have a node between everything. Which is going to be this here, where you basically have a radical in every position. This doesn't really happen. This molecule will probably explode before it actually got to this point, but it is theoretically possible. There's kind of an imaginary line in energy here where you go between having double bonds and breaking them into single radicals. If you heat these compounds up as much as you can, you end up in this state where you have this kind of pattern where they'll have double bonds, but they're just gonna rotate every double bond. If you add light into the system, you can actually push it over into this next part where you start getting these single electrons by themselves. So I'm going to do some bigger examples. And then we're actually going to jump to some reactions which are not really related to these, but we will get back to them on Wednesday. So let's look at a 6-electron system. So for a 6-electron system, I need to have 3 double bonds. Our lowest orbital system is going to be, it's always the same thing. Oh, I forgot to mention this last one. This area where you have either the isolating ones or you start to have one, this is where chemistry happens, usually. So these are the ones that we're going to care about. So I'm going to be mostly focusing on these guys. Okay. But just to draw on the lowest one, give you an example. Lowest one's always gonna be the same. This equates to all of our electrons being in the same position. This is our nice has resonance system. I'm going to end up skipping our first one because our first one's a little bit odd. So I'm going to go into what happens when we heat this, and we kind of get to our imaginary line that we had drawn earlier. So that's going to be where we have these rotating at every double bond. So pair of two, pair of two, pair of two here. You could equate this to drawing it on your molecule like this, which is what we're going to end up doing later. So double bond, double bond, double bond. Versus if we throw light in here, we're going to push this over to where we start having the single radicals. So there'll always be the two radicals on the end. So it's going to be one by itself. A pair of two, a pair of two, and one by itself. I'll kind of go over this pattern in a second. I'm going to keep it green. One by itself, pair of two, pair of two, one by itself. So for drawing these, the bottom ones are going to have a general pattern. I call it 2n. Really, it's just pairs of two. N doesn't really mean to anything. You're just going to do pairs of twos until you run out of space. For this one up here, it's going to be 1 plus 2n plus 1. So essentially, you're going to have an electron by itself, as many pairs of two as you can get. And at the end, it's always going to be 1 by itself also. Because these are always even numbers, you're always going to end up with a 1 in here, a 1 here, as many twos as you can get in the middle. So let's look at 8 just to do it. I'm going to draw this in a little bit more of a way that we're going to see it when we start doing these reactions. So for an 8 electron system, there's two different ways we can draw it. We can either draw it like this, or what we're probably going to see, because these are going to involve cyclizations, is this here. So they're the same thing. This is just a long chain version of it. This is kind of a coiled up version of it. When I throw heat into my solution, it's going to put it into a position. So I'm going to redraw this out and draw the orbitals in. So we have 1, 2, 3, 4, 5, 6, 7, 8 positions that have double bonds. So 1, 2, 3, 4, 5, 6, 7, 8 here. With heat, they are going to rotate every two. So we'll have a pair of two on top, pair of 2 on bottom, pair of 2 on top, pair of 2 on bottom here. And then I'm just going to redraw that on our cyclic molecule, which is what we're going to be dealing with when we actually get to these reactions. Okay, so same concept. Now we're just going around the circle this way as opposed to going in a straight line. So if this is 1, we'd have these 2 that are together. These 2 down here that are on the bottom, these 2 on top, these 2 on bottom. And when we actually get to reactions, the reactions are going to be occurring between these 2 endpoints coming together, but we're going to talk about that later. So with light, this followed the pattern 2n, it's every 2, we switch positions. When we throw light into solution, so H nu here, so we'll draw this out in green. Our pattern is going to end up being 1 electron by itself. Yeah, we can do that in red. Okay. Pairs of 2. Pairs of 2 on top, pair of 2 on bottom. And at the end, we end up with 1 by itself here. Okay. Same thing for this one. It's just a cyclic form of it. So we'll have 1 electron by itself, a pair of 2, a pair of 2, a pair of 2, and 1 by itself. And if you look at these, they end up different at the endpoints. But we're going to talk about that later. I'm going to kind of move on from this because this is kind of where your book stops and changes gears. So we're going to switch to a different reaction, which kind of involves this, but really doesn't really get going until we start talking about the Thiel-Faldo reaction. So we're going to pause on this molecular orbital theory and switch over to some 1,2 versus 1,4 reactions. So these are based on a concept that we learned a while ago, which is if you add HBr to an alkene, you get H in this position, Br in this position. If we were thinking of this, we could call this a 1,2 addition. The H and the Br add to the positions that are next to each other. If we take the diene version of this and add an HBr, this is going to complicate things a little bit. There's 2 different possible answers that we can get from this, and it is going to depend on our conditions, whether we are in really cold conditions or in room temperature conditions. But I'm going to go over those in a second. So I'm just going to start with talking about what the 2 possibilities are. So we can, if we were to protonate that same position, we would get a positive here, and Br could come in, attack at that positive position, we could brominate, and this would give us another 1,2 addition. Like before, 1, 2, 3, 4 here. The other option is that we have resonance. So these electrons could potentially shift over. This would give us a different carbocation. With a different positive charge, at which point Br could come in. And give us what's going to be called our 1,4 addition product. So our 1,2 addition is where we have our alkene attack this H here, Br comes in where the positive is. Our 1,4 is when we have resonance happen. It's going to shift the double bond over, and they're adding 4 carbons away from each other. Or I guess technically 2 carbons away, but they are 4 slots away from each other. So before I talk about those, I'm going to talk a little bit about double bond stability, which is something that you guys probably got back in chapter 8 at the end of OChem 1. But just as a review, your double bond stability looks something like this, where your least stable one, I just write H's here. Your least stable double bond is just hydrogens. And then as we start adding in carbons, there's a bunch of different di-substituted ones, but I'm just going to give you the trans one. Tri-substituted. And quaternary substituted is going to be our most stable here. This is going to play a big role because in terms of carbocation stability with resonance, normally we think of like this positive charge versus this positive charge. This is drastically more stable. For the positive charge. When we add in resonance, these 2 positive charges are actually pretty negligible. It's not dramatically, it's pretty, like almost no stability difference between this positive here and this positive here. But on the other hand, this double bond has 3 substituents to it, versus this double bond has only 1 substituent to it. So this is a dramatically more stable double bond. And because of that, if you were doing a reaction that had resonance, this would be your major product. versus this one over here would be your minor product. Okay, so let's throw these into some reactions. I'm going to start out with cold conditions. And essentially at minus 78, this is going to be too cold for resonance. You do need some sort of energy in order to do those shifts. To occur, if we're thinking about protonating these, there's technically 4 different options. I'm going to go over the really kind of simple ones first. So I could either get protonating here versus here. This one on the left that has no resonance at all. There's no stability effect to it. This is basically not going to happen. It's just dramatically less stable. Even if it's not warm enough to actually do resonance, having that double bond there provides a lot of stability. So these, where we don't actually have any resonance, they just don't have it. If I compare, I'll draw these in blue and hopefully they show up. This center versus this center. So we're going to ignore putting the positive here because that's the same thing as putting the positive here. It's not going to have any resonance. We can either get oops, that's the same thing, just flipped over. These two here. We're going to follow the same rules as we have been following, where you're going to want to add it to the more substituted center, especially for this initial attack. So we have a tertiary and a secondary. This is going to be our major product. We're not really doing any resonance in this case, so this can have bromine come attack it. We're going to have BR add to our more substituted center up here. And then that's all that happens with these. So in cold conditions, you're just kind of comparing your 2 double bonds. This one's got a tertiary center to it. If I protonate it, it's going to lead to this product here. I'm going to talk about some warmer conditions, and then we're going to kind of stop there for today. So at room temperature, your book puts 40 degrees, but really you can do it at probably 25 degrees, which would be room temperature. But I'm going to stay consistent with the book. So HBr 40 degrees Celsius. We're doing the same thing as we were before. We're going to make this positive charge here. From this point, we have to consider resonance. Because we're at 40 degrees, we're at like a normal temperature. This can move over. and also give us this option. So for this option here, we have a double bond with 2 substituents on it. For this one, we have a double bond with 3 possible substituents or 3 actual substituents on it. That means this is our more stable double bond. And this is going to lead to our major product. So to review these, in cold temperatures, we don't care about resonance. We are just going to do kind of a normal addition where we're going to want our positive to end up on our more substituted of these positions. We're going to get a bromine here. This is our 1,2 addition versus at room temperature. We're going to actually care, and we're going to want our more substituted double bond to be prevalent. So we're going to end up getting the 1,4 addition. On Wednesday, we'll do some more complicated examples. We'll do stuff with like, if I have substituents here, when we do resonance, we have to actually compare which is our more substituted double bond and figure out where the actual best product is going to end up. So this is where I'm going to stop for today. On Wednesday, we'll start doing some more complicated versions of these and get into the Diels-Alder reaction. And yes, I will update everything during office hours today for the schedule and the. Oh, and your test will be available Tuesday afternoon. I'll also post a key.